Welcome back. We're starting the design of the sequential circuits. Like I said, we'll be first focusing on a general methodology, just like we did in combinational circuits. Then later on, we'll be using that methodology to design some sequential circuits. But as I expected, the methodology here is going to be complicated, right? Because we have to consider two things. First, the current inputs, which is straightforward, that's not a problem. The problem is the second aspect of it. We have to also consider what are the previous outputs from this circuit. And those outputs, as you know, we store in the feedback path using a memory. Now, memory, we have discussed how to store bits. So for a particular state at a given instant of time, the circuit will be in some sort of a state, fine? And that state will be stored as a binary information in the memory that appears in the feedback path, right? So the memory in a sequential circuit, it stores bits, and those stored bits will represent the state of the circuit at any given instant of time, right? And we can actually come up with a methodology based on this state of the circuit to design the sequential circuits or to design the circuits that have a specific behavior over time. In other words, what I'm trying to say is you have a sequential circuit, its behavior changes with time. Now, an important thing here is that the notion of time in the sequential circuit, it is the clock. If you remember the latches and the flip-flops that we discussed, except for the basic SR latch, every other latch or flip-flop had a clock. So the notion of timing is clock, and a sequential circuit at a certain number of clock will have a specific behavior. As the clock proceeds, the behavior will change. Right? So what we try to do in the design of the sequential circuit, we try to exploit this concept of state. We choose a time interval, which in this case means we choose a clock period and capture the behavior of the circuit in this clock period as one state. Then the next clock cycle, behavior will change, capture that as a second state, and so on. Then we make a list of these states, we make a sequence of these states, and then using those states, we actually design our sequential circuit. So the concept of state is central to the design of the sequential circuits. And we use an approach that's known as the concept of finite state machine. It's quite literal that we design a machine. Machine here means a sequential circuit, which is based on the finite number of states. And as I said, state means the behavior of the circuit in a certain clock interval. Fine. So before we actually can discuss that methodology, we need to understand how do we capture, yeah, how do we come up with these states. Yeah, in other words, how do we come up with a finite state machine for a particular circuit behavior so that we can actually design it, right? And to put forward this concept, this is going to be an extremely important concept. If you understand the concept of finite state machine, then only you will be able to design the sequential circuits, right? So we'll spend some time on this concept. I will take some small elementary examples, and then we will build on that. For starters, a finite state machine, FSM as an acronym, as the name suggests, it will consist of a lot of things that will come, but one and the foremost thing that it will always consist is it will have a set of states. Again, I have originally defined the state. State is the behavior of a sequential circuit in a certain clock interval. Right? So if I take a simple example here, let me define a system. So just to put forward this concept of finite state machine. So let's consider a system, a simple on-off system that repeatedly sets an output. Let's denote that output by a variable x to 0 for one clock cycle and then to 1 for one clock cycle. simplest of the scenarios. So this typically is a circuit which has two behaviors. First behavior is in a given clock cycle, its output will be zero. So we'll be capturing that behavior in one state. Let's call it off state because output is zero. Then when the next clock cycle comes, the output is one. So the behavior changes in the next clock cycle. And that behavior we can capture in state, in another state. Let's call that state on. And every time a clock cycle comes, you actually move to next state. Right? So it is something like this. If I try to show it using a timing diagram, if I have a clock here, this is one cycle, this is another clock cycle, third one, fourth one. Fine. Henceforth, we will be assuming a flip-flop behavior, means triggering will only happen at these edges rather than the levels. Fine. So this is my clock. And if I try to draw the state here, again, as we have been doing, let's draw the projection. So here is what my circuit will react to, the positive edge of the clock. Right? Now, as far as state is concerned, in the first clock cycle, my output is zero. So we will call that state as an off state. Then in the next clock cycle, the state will change and we'll call that on state. Then in the next clock cycle, again, it will go to the off state. Then in the next one, again, it will go to the on state and so on. Fine. This is the behavior. So as you can see in the first clock cycle, the behavior is off. In the second clock cycle, behavior is on. And I'm capturing this behavior in terms of two states, an off state and an on state. And we can also draw the output here because in off state, my output will be zero. So it will be a low pulse. In the on state, it will be one. Then in the off state, again zero, and so on. Fine. So this is my output, which I am referring here, X. So this is a typical timing diagram. We are working our way clock by clock, and the behavior of the circuit in a given clock is captured as the state of the circuit. Fine. Now I can represent this behavior in terms of a finite state machine. Now clearly here I have two states. My first state is the off state. So I will draw a state, normally draw it with circles, and call it off. Then I have second state, I call it on. Fine. In the off state, my output X is 0. In the on state, my output X is 1. And every time a clock happens, I actually move from off state to the on state at the positive edge of the clock. Then another clock happens, I move from on state to off state. Then another clock happens, again I move from off to on and so on. So this timing behavior actually I have captured in terms of then this is a finite state machine. We also show a small arrow here that represents, because for analysis I have to consider one of these states as the starting state. So I'm assuming here that off state is my starting state and that I represent by a small arrow. Fine, so simple concept. Now if I extend this concept, and let me assume that I have a same circuit, but in this circuit, we have one off state followed by, let's say, three on states. Fine. What I mean by that, I have a first clock cycle. The behavior of the circuit is that it outputs a 0. Second clock cycle, the behavior of the circuit is it outputs a 1. Third clock cycle, the behavior of the circuit is still that it outputs 1. Fourth clock cycle, again the behavior of the circuit, it outputs 1. Then at the arise of the fifth clock cycle, the circuit behavior of the circuit changes and it outputs 0. Now in terms of a clock, a timing diagram rather, it is something like this. Again, I will draw a clock signal here, a first clock, second clock, third clock, fourth clock, fifth one, sixth one. Like I've been saying, this is the edge where my circuit will respond. So this is clock. Again, we'll draw the projections. Fine. Now this time round, the behavior is something like this. First clock cycle, the behavior is that the circuit is outputting 0. So this is off. Next clock cycle, behavior of the circuit is it's outputting 1, so on. The next clock cycle, again it's outputting a 1, so on. Then somewhere here it changes. So it's something like this. Off, let's call this on 1, on 2, on 3. Fine. So for the 3 clock cycles, it's outputting a 1. Then it goes back to off, then again on 1, and so on. You may also want to plot the output here. So output will be in the off state a low pulse, in the on state high pulse, high pulse, high pulse, then a low pulse, then again a high pulse, and so on. Right? Now, if I am to capture the finite state machine for this circuit behavior, this is state, this is output X. Right? So this time round, I have 4 states. Again, I will draw the circles. State 1, which is my off state. Second state, on 1. Third state, on 2. Fourth state, on 3. In the off state, my output is 0. In the on 1 state, my output is 1. In the on 2 state, my output is 1. In the on 3 state, my output is 1. As far as transitions go, if I have to move from off to on one state, a positive clock should happen. And again, from on 1 to on 2, another clock should happen. From on 2 to on 3, another clock should happen. And then from on 3 to off, another clock should happen. Fine. And for analysis, let me assume this is my starting state. Fine. This is the behavior of the circuit. Fine. We'll continue with this example in the next video.